Yeah, so hello everyone, if everybody watching. I'm Nishant, and today I'll be taking the a class on algorithms on behalf of the online math club. So this is the buffer problem. If anybody wants to have a look, they can. If everybody's done any of the problems before or they're ahead, like they can just like do that. I hope everybody got a screenshot. So also it'll be nice if you unmute and because like it'll be hard for me to see the chat in this setup. So okay. Fine. So we'll start off with the first problem of today. So the plan for today is to mostly keep it like problem based. Like we'll mostly be doing like math based algorithm problems. So the main algorithms you have is like greedy, like that is one. That's like the one of the common ones. And then like the rest essentially like
Take
so
emotionally.
sorry. Hello. Okay. The rest like so everything else like you can literally group under one bracket because you need to be a little bit innovative and creative about like how to create the algorithm. So I'll just like give an example of like greedy while before we start off with the other things. So let's do this first. So I'll give everybody like 5 to 10 minutes to try it and then we can discuss ideas. Oh wait. Oh. Also, it would be nice if we keep it in kind of like a group solve kind of class so that like everybody manages to interact and participate. So let's do that. So this will be the first problem of today. I'll give you all 5 minutes to try and like at least read the problem and before I like start explaining anything.
Someone is asking what greedy algo.
Oh, okay, I haven't defined it. Okay. Okay, so actually let's like do this problem first and then I'll like define it or whatever we or like it'll be more intuitive if you like just do it and then you learn the definition. Okay, let's see the chat. Like you just try this problem and then like if you are stuck, then we can like do that. Time. Also, if you have any ideas, you can just like speak or like if you want to chat, like if just like Mandar, if you can notify me when like somebody like says or like anybody else, just tell me so that I have a look at the chat. Okay. Ayush, right? Okay, I think I've seen your chat. Okay, so what are you saying? If we can take multiple lines from the same point and select a point. So you've gotten a line here, L2, and select a point. Okay, so I would like to understand what you mean by select a point. Like, I don't understand really what you mean to say through this message. So I've taken a point here, I've taken multiple lines, but what do you mean by selecting a point after that? I think it has been 5 minutes. So any ideas or anything? Ayush, like, can you like, okay, we select 2 points. Okay, okay, fine. If we, okay, Ayush, if you can't unmute or like, if you are more comfortable, or do you want to be more comfortable chatting? Like, unmuting will be easier for me to understand what you're trying to say. We select 2 points. Okay, convex hull. Okay, I need more explanations than just 2 words. Everybody, okay, let me 1 second, Ayush. If we, point, 1 second. So if we take multiple, yeah. So you have line one. You selected 2 points, and you select one from line two. Okay. How? Okay, you just select it and then you do. Okay, I think I have to like wait. It's saying. That's okay. Yeah, that's correct. Rudransh, that thing is, you do have that, but I don't know why it will be useful. Like if you can use it, that'd be nice. If you select 2 points from line one and one from line two. Yeah, so I have select, okay, sure. So we select A1 and A2 from line one, and then B1 from line two. Then like, okay, so you just keep on, how do you know you'll get 100 points? Like you'll have to like give me a more concrete reasoning than that. Like you can do that, but okay, say you pick one more on this line. And then like this gets like collinear. Like how do you guarantee that this does not happen? Sadat, can you like explain your idea more? Then we select C2. Okay. We have a C2 here. You can select the C2. But I think you have to define the algorithm better. Like, so, okay, let me just write down the steps for the algorithm. Pick a point A1. Oh, yeah, we have an A3, right? On almost every line. A point. Let's not call it A1. Let's call it just P at this point. P, the point P, to then what you do is look at a line through P with at least 1 point on it. Yeah, so Ahan can like explain. Like either you want to chat or like you want to unmute, like please go ahead. Okay, wait, why is this lagging? Yeah. Then the third you said was if possible, pick the new point. Now the question marks here are where does this algo end? And how do you know it like ends after 100? Like after picking 100 points only it ends. So yeah. Ahan, if you can like explain your idea. Okay. Yeah, so that is essentially the main idea. Let me just like explain it to everybody here. So essentially the algo we wish to define is one, uh, pick some point. Okay, wait, defines which is not in set A, not in S. You've not picked it till now. And is collinear and is not collinear to any other point. Collinear with two other points in S. Second, uh, keep on doing so until stuck. So this is called repeat until stuck or rust. RUST. And so, as Ahan said, say you have, so instead of like explaining the 99, say you have n points when this procedure ends. And you can't pick anymore. So now like you have this set of n points and like for any any two lines, any two like any point outside this set, say, there's a line passing through it from these. So you pick say an A and B and inside this set and you have an X. So then there must be some AB whose line passes through X. So that means that the number of points like outside the set S, as Ahan was saying, which is like should be less than the number of lines which can come out of the set S, choosing 2 points at a time. So essentially we have that n choose 2 is greater than equal to 4951 minus n. I think that is what you're saying, Ahan. So I will leave it like this is like now after that, like this is nothing much to do, like n into n minus 1 by 2 greater than equal to 495 1 minus n. And then now I think like all of you can just like resolve this equation and then get that n is greater than equal to like 100. And then only the algorithm ends. Yeah, since there are no as answers, since there are no four collinear, wait, Ahan, like, do you want to explain why no four collinear like is required here? Like, why do we need, why do we need the condition that no 4 points are collinear? Like three of them can be, but four of them is like not allowed. Like, why do you need this condition? Wait, let me like. Okay, okay, so let me like frame that hopefully better. So like the thing is, we wish to kind of like for each outside point, OI, call it outside point I, you want to map like two other points in S1, SI, comma 1 and SI, comma 2, which are collinear with OI, right? So like it's kind of like a function where SI, comma 1 and SI, comma 2, or like, or even let's just define it in reverse. So like you can think of it as like a function from points to like S square, like points. So let's name it points not in S to S square, where like f of OI maps to SI, comma 1, SI, comma 2, which is like a tuple or a list in computer language. So yeah, let me just like finish this. So the thing is key if say so now the thing is each point must have a different each a unique line, because if say two OI like say O1 and O2 had the same line, will lie on the same line, then like you had 4 points collinear. So like it's not possible. So this means that the you need like for like so the number of possible S square, like the number of possible points in S square must be like greater than the number of like elements in P minus S. So like so that's why we get that inequality that NC2, which is like mod of S squared, not S squared so to say, but like S into like S minus that itself, so like S squared is greater than or equal to like P by S mod. So that's why we get the inequality which like solves it very nicely. I think as Rudransh mentioned, like it's like 4951 is equal to 99 plus 98 plus dot 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 1 plus 1, which is like 99 into 100 by 2. But like so getting this thing won't actually help you, I would say. Like the more important fact is noticing that it is 100 choose 2. So that's why it works out. And we have this very specific number. Okay, so I hope everybody understood what the idea in this problem was. So now let me just define what is now let me just like explain through this problem what we meant by greedy algorithm. So essentially at each step in a greedy algorithm, like what we are doing is we pick the most optimal choice at each step, or keep on picking something until you get stuck. So these are like two kind of broad categories you can think of. So in the first one, like you keep on picking the most optimal choice you think till like you get stuck at some step, and at that point in time, you will just need to show that you've gotten like as much as the question wanted you to get, essentially. And in the second one, like this is This is exactly what we did in the problem here. So we just did this kind of algorithm here. So we just like kept on picking points until we got stuck. And then like once we got stuck, all we did was show that since we are stuck, like we already have like maximized the set of required points, which is like what the question wants. So that is what we mean by a greedy algorithm in some sense. It's not a full-fledged definition, but like I think this gives you an intuition of how a greedy algorithm works. I hope your doubt is answered, Ayush. Okay, that's nice. So we are done with this one. Now let me find another problem. So wait, give me a second. Yeah, let's try this. I think let's paste it here. Let me just paste it on the side. I hope everybody can see the problem. Yeah, we don't need this really. Oh wait. And this is also not important. Okay. Sure. So now so here is the next problem. So I'll let you all try it for like 5 minutes ish. 5 to like 6 minutes. And let's see if anybody has any ideas. So also I want like more than just Ayush interacting. Like it's not nice to have only like one student when we clearly have like 9 participants. Okay. I mean, like being late is a superpower in itself. So like, don't worry. So I'll just like recap what we did. I hope. Wait, did everybody get a screenshot of the problem? Okay, I will assume like you guys got to look at it at least. So all we did was like we discussed like a example for greedy algorithms. So essentially, like this was the problem. I can like post it in the notes later. I'll take screenshots and I'll like send it in the OMC group. So like this is the problem. If you want to like try it after class and others and stuff, so like you can take a screenshot. And I explained essentially what through this problem I explained what like a greedy algorithm is. So what we do in a greedy algorithm is like we keep on picking the most. Uh, 1 second, Ayush. We like keep on either picking the most optimal choice or we like keep on picking something until we get stuck. So essentially, the most important step is like when you get stuck, like what you do. So in a greedy algorithm, we just pick the most optimal thing. So that's all that is intuitively there in greedy algorithm. Okay, so now I hope you understood like roughly what you're doing. Bratajit, if I'm pronouncing it correctly. So yeah, Ayush, right. Cindy has 100 and yeah, exactly. So she has 100 in these weird denominations, American denominations. which are like pennies, which is like, so a penny is written here as like 0.01, a nickel is 0.05, a dime is zero point 0.1, and a quarter is 0.25. So it's like in some random assortment of this thing. Yeah, the naming is also noticeably American. So, yes. Any ideas you can like just like send in the chat? I shall try to see it as soon as you send it. Or you can like talk and like unmute. I'm fine with either. Also, if at any point I'm going too fast or going too slow, like just message or like unmute. Anything's fine. I'll give you all another minute or two. Okay, it looks like we have, yeah, okay. Okay, nice. We've gotten an idea. Okay. So Swarnava, right? Or am I like, is it like Swarnavo? Like, I don't know the pronunciation. So your idea is like roughly, thank you. Right. Nice. Somebody who tells me not to worry about the names pronunciation. So anyway, you are saying that we add pennies, which is essentially like 0.01 to like one of the sides. So essentially like plus plus dot 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 plus until we reach like $50, in which case we're already happy. So like 0.01 into like if we have like greater than how much? 5,000? Wait, okay, yeah, I think so. So like we will need 5,000 pennies roughly to like get the $50 if we are lucky. Like greater than equal to 5,000 pennies and we are happy. But like the bigger question is like what happens once the pennies end? So you've gotten like X pennies and like you've got to make what? You've gotten like you finished up your like stock of pennies. So now that is the question. So what will you do then, Swarnama? And you still are like away from the $50 mark or whatever. This is a good idea. It has some premise. It's good. But like the thing is like how will you like handle the 50, like how reaching the $50? Okay, so now we just add the next denomination. That yes, let's do that. So thing is like once you add pennies, say you have like 27 pennies or something, some weird number. So first is like, can you have 27 pennies or like anything of that sort? Because if you have say 27 pennies, like since you're adding like 0.05s or whatever, like eventually like you'll probably reach like 49.9 97, and then you'll go to 50.02. So like, why? Why do you think that will work? Okay, yes, that is correct. So as Ahan mentioned, it would be a multiple. Yeah, the number of pennies is a multiple of 5. Yes, correct. So we cannot have 27, in fact. The number of pennies should be a multiple of 5 because like we have say xp pennies, like p into 0.01 plus uh how many, okay, so nickels is an n, 0.05 plus total number of, what's the next currency? Dimes and quarters, okay. D into 0.1 plus Q into 0.25. So this total adds up to five, sorry, not five, $100 in our question. So she has exactly $100. And let's just like multiply by 100 to make our lives easier. So like this becomes like 10000. This becomes like 5. This becomes like 25. This becomes like 10. So essentially we have that. Wait, let me go to this side. P plus 5 N plus 10D plus 25Q is equal to 100,000. Oh, wait, no, 10,000. My bad. And now, if we just like move the thing over there, P is equal to like 1,000 minus 5N minus 10D minus 25Q. And this is clearly divisible by 1,000. So as it has been mentioned, like this is a multiple of 1,000. So this works out. Correct. Right. Now that you do have this, okay, say you run out of 0.05s now, is the question. Now it comes the tricky part, I think. So you ran out of 0.05s, you've gotten like, okay, so let's just change x to like 5x now, since like so everybody got that we must have 5x. Now, once we run out of 0.05, you would like to, yeah, so I'll give me a second, Ayush. So you would like to like add the next one, right? So the thing is, what, how do you know that 49, like you reach 49.95 and you like run out of this, why, like whatever, what do you call it? What do they call it in the question? Nickels. Like you run out of 0.05s and you reach 49.95. Then like as soon as you add like the zero point 0.1 thing, like you will jump to 50.05, which is not what you want. So can somebody try thinking why this will be thing? Okay, you can remove 0.01. Okay, but it's also like now you're just like trying to like remove stuff. So like what if like x is equal to 0? So like you can't even remove like 0.5s or whatever. You can't even remove like 5 pennies. Like the next idea was remove stuff. So first we like add until stuck, and then we did like when stuck remove. So like I kind of want all of you to like think of roughly like how would you like phrase your algorithm, because while writing like a solution, if you're ever writing in a contest, like you will have to like phrase it in some decent form. So I think it would be nice to start practicing from now. So thing is like you can't remove so if you remove stuff, like you are not sure ki does that thing even exist while you're removing it. So that's the question. Okay, so I'll again give you, and I'll give you another minute. Okay, we got another idea. Okay, sure. Fine, I'll give you. Okay, so all of you are on the. I think our minute has elapsed. So I don't see any other ideas coming. Really? Uh, just interrupt me if you have any idea or like send it in the messages. Yeah, now. Okay, so now you have this when stuck remove, then add. So now like your algorithm gets more and more convoluted. Yeah, so now you're stating that you will approach 50. Like, how do you show that you'll exactly reach 50 using this algorithm? Like, you have to have like a method to show that. You do realize. Come on. Like, you can't state. Okay, so the current question is like this. So like the pennies thing, and now the thing is like what's the Shaurya was saying that you just add until like you cross 50, and then as soon as you cross 50, you like remove something. If it goes under 50, like you add something back. Like my question is, how do you know it terminates this algorithm? And how do you define it like better? So saying we will approach 50 is like not correct because like this is like not it's not like a continuous function or something, so like it's discrete, so like it will like shift by a decent or considerable amount which you can't like quantify. Approach 50 is like wrong, you can't just say that. So yeah, so now I will try to like, so now what if, okay, let's just try this. What if we like try adding like the other things? So like when all of you know, right, like when you give change, you like give the largest change first. Like for example, if I want to give like rupees hundreds or like 500. Yeah, exactly. So Ahan's thing, right? Ahan's idea is like correct. So like when you want to give change, for example, like I'll just give an example. Yeah. Like you just if you have a 50 rupee note, like you'll probably want to give that. Or if you have a 100 rupee note, even better. So like you check if it's if there's a 100 rupee note. If yes, give it, and they're done. Exit. Else, like you check if you have 50. And then if you have 150, you look for like if you have 25s, or if you have like 250s, you just give it. And so like what we do is we look at the largest denomination, which is like Ahan's idea. But and now what we were trying earlier was looking at the smallest denomination. Wait, let me zoom in. Smallest denomination. So I hope like you can understand like why. Now let's see why it would be better to pick the largest denomination method first. So essentially like what we do is wait, let me yeah. So let us say we add 25s. Wait, 0.25s, whatever. Okay, since we are lazy, like multiply everything by 100 and then we add 25s. So our denominations are now 25, 10, 5 and 1. And we managed to make 100,000, like 10,000. I hope everybody understands like we can like scale it by like a factor of 10. I mean 100 to like make all the changes like work. So, okay. Now essentially we add like 25s until like we cross. So now our aim is to reach 5,000. Yeah. So we add 25. Say we add like A into 25. If A is like, if we add all the 25s, keep on adding 25s until we like reach 5,000, at which point we're happy. Reach 5,000, happy. Else, the number of 25s ends. Yeah. So like once you finish off the 25, so what we do is like we just pick the next one, which is 10. So like if we like reach 5,000, we're happy. Else like the number of 25 ends. So like we add tens. Now, here the thing is, we have to be a little bit careful because say you have only like 125 and then we like keep on adding tens. And then at one point, like we reach 49 point, like 4995. And then we move to like 5 triple double zero five. You can't send pictures, what? Yeah, yeah, exactly. So if it crosses 50, like because we are picking the pennies one by one. Okay, so Anirudh, your question is like we have 25, but they would exceed 50. So if it crosses 50, then like we are already like happy because like at some point it'll be like less than 50, like it will be equal to 50 exactly. Since we are picking exactly one at a time in like the only 25 case. Here, here the thing is like if we have an odd number of 25s, so here if we have an odd number of 25s, this is possible. Like having this happen is quite possible. Like you move from 4995 to like 5005. So to like escape this catch. Yeah, exactly. So the thing is that as Shara says, so we will have to have pennies and nickels at this point because if we only had tens, say, then like odd times 25 plus like k times 10, like some number of tens is equal to like this, which is like this is odd, this is even, and this is even. Like this is not possible. So we must have like uh nickels at least definitely. And now like you can just keep on doing this like contradiction thing. Like you assume that like your now that you have nickels, like you can like either remove the 10 and you'll be happy. Like you can like take out a 10 and put in 1 5 if you like reach 5005. Or like if you don't have, if you like run out of nickels. So now the question is, what if you like run out of thing? Or what do you call it? Uh, dimes. And then you'll go to nickels again. The same idea until like you reach like 50. And now the thing is like you will have to reach 50. You cannot like cross 50 in any way. Like if you you'll only like not reach 50 if like the number of pennies is like greater than like the $50. So essentially what I'm saying is like you can just keep on picking like nickels until you reach else stop. Else like you've ended. At which point you only have pennies, and then pennies is like all good. So like you're done. So I hope like everybody understood like how this works. Right. So again, so the here also the idea is like greedy. It is like a greedy algorithm. And here like we did not we had to care about like how we go about picking the coins. So we picked so this type of algorithm like it comes in the first thing like wait let me like show where I read that. Yeah, we have it here exactly. So here we like pick the most optimal choice, which was like largest until like you are like you cross 50 or something. You pick the largest denomination until you cross 50. That was the most optimal choice. And like you repeat it until you are stuck, at which point you showed that you are not doing like you can optimize your moves to win. So that is this sort of greedy algorithm you can think of. Right. So we have okay, so now let's do a slightly more difficult problem. So now that we've done like two, okay, so we've done two problems of what? Greedy? Wait, do I have, where did I write that? Yeah. We've done like two problems of greedy. Wait, let me just come here. Yeah. We've done like two problems of greedy. So like let's try a miscellaneous type of problem now. Where's the, so essentially like Okay, you'll see the leap of faith thing like more otherwise, but usually in algorithm problems, like it is like very rarely written that show that it is possible. It is like really rare that this is like written show that is possible. So most of the time it's written determine whether it is possible. So essentially the leap of faith is hoping that you have an algorithm. So like these are like very so both of them like both of these questions like literally ask you to like show the algorithm explicitly. Like they tell you that there's an algorithm and all you have to do is find it. But most of the time, the question is like determine whether there exists an algorithm. So like we'll see one sort of problem like that now. So this will be a slightly harder kind of problem, but like it's okay. So let's pick, it's kind of famous. So like if anybody wants a buffer, like which is not the given buffer problem, like I can give you one more. Let me go back to yeah. So now let's do a little harder problem, slightly harder problem. So like this is all unnecessary details. Nobody sees this. Nobody sees this as well. Yeah, let's start with this. Okay. So now I think I should actually give you like 10 minutes to like try this problem. So like here, yeah, yeah. So now I remember I think Ahan who like asked about leap of faith thing? Yeah, okay. So here you can see determine if there exists a finite sequence of operations. So like you might think it's a no or a yes. You have to be like in a contest, like you won't be told like this is an algorithms problem. Like right on why like how I'm telling you now. Okay, yeah, this is also in Rishta's book, but it's a really instructive problem. So if you've done it, like I'll be glad to like have you seen the buffer, Anirudh? Or have you done this problem? Or do you remember the solution? Like done doesn't matter. Like if you remember it, it is. I will show you the buffer. Else, like you can try it. Okay, you don't remember. Okay, that's nice. That's nice. So you can just try it. Wait, you forgot how to do this, or like you forgot to do this at some point in your life? Okay, okay. It's okay. Like if you like, you can just try this. Like try like refinding the solution. If at any point you like have found, if you like find the solution or like you get the most idea, like you can stop and let others try. I think that sounds fair. Yeah. So I'll give you like a 10 minutes trying time. I think this is actually like harder than as compared to like the other problems. But like I wanted to introduce you to this type of problem as well. Like so like essentially like I'll just give you a bit of uh mathematical basis. So the thing is no type of so the yes type of problems comes under algorithms, which is what we are discussing today. This unit is okay, I will write. I think it is DCYIY. It's named that, but it's actually algorithms. But like, yeah, like the unit doesn't matter, honestly. Like, just try the problem. Like, if you do it like as long like you'll have the unit right. Like, do the problem like you'll have like done one problem in the unit, which like saves you time. Not only that, it's like a required problem. So like it's instructive. Okay, so now, so the yes type of problems where like you think that there exists a finite sequence of operations, you give it to them usually most of the time. So you just like explicitly define. define the algorithm. Else, you like show that there exists an algorithm. Much like Hall's theorem, I think you all must like there has been OMC class on Hall's theorem, which like it like tells you that there exists a perfect matching. It does not give you the perfect match. Okay, yeah, that is so right. Yeah, so the fact that you can figure out whether it's a no or a yes itself is like kind of hard because in a contest, like you won't be given this information beforehand, and like if you like spend too much time trying to know when it's a yes, you've like lost a lot of time, and then like that could be detrimental. So like figuring out whether it is a no or yes itself is like a tough thing in itself. So yeah, so the yes part comes under algorithms. The no part comes under processes, which is like you look for an invariant kind of. 1 second. You either look for an invariant, observe the process, like you just make observations, observe the process and why it should fail, and why like it fails, or something holds. And like the third type is like you look for like too large for an algorithm to reach. So essentially, like these are two philosophies of problems, you can say. And like both of them like kind of go hand in hand in the same question also sometimes. So like they might ask you like find all, so instead of like this, find all numbers which can be reached. In which case like the numbers which cannot be reached will become a processes question, and the numbers which can be reached is like an algorithm question. So like these are two philosophies which will be nice to keep in mind. I hope like you understand what I'm trying to say. So yeah, so we have this. Okay, now we have a huge number that is agreed. But yeah, so essentially like this number is probably not relevant. It's just that the size of the number is relevant, is what you can think of, because clearly 2010 is like redundant IMO things. Like that's why it's there. So yeah, I hope all of you understood like what philosophy I was like trying to explain. Yeah, so you like now I'll give you another like 2 minutes, I think 2 or 3 minutes more before like we start like trying to like get into like the process of like how we can try something. So I think we have done our 2 minutes. Any ideas? So like any ideas on base cases? I think I hope you all have tried base cases or something. So any observations in base cases of some sort? Okay. Okay, the place that yeah, yeah. Okay, okay. So all n works. Okay, nice. That is some all n greater than equal to 6. Okay, all n greater than equal to 6. So we let this number be like capital N or small n. Okay, let's just write small n. I'm too lazy to write capital N. So claim. I think we should write down. Wait, can I not move this stuff? Okay, I'll just like copy paste the question. Wait, what? Can I not copy paste question? Okay, leave it. I'll just paste the question again. Okay, this is not required. Oh, and the 2010 is obviously because of this. But yeah, so now we have our first claim of the problem. Claim one. This is not 2010, and this is n. All n greater than equal to 6 works. Right. So, okay, nice, nice, nice. Okay. We have some. Okay, that does stop. Okay, okay. How about this? Like, let's start with like. Okay, so now before we like get into all that like huge thing, let's start with 111. Like, I don't want to start with like six things and let's see how much we can maximize here. I hope that sounds fine. So does anybody want to tell like how we can maximize this? Okay, so I will write this as B1, B2, B3. Empty the first one means 0, 3, 1. Is that correct? Yeah. Okay, nice. Then what do you do? Like in three cases, it's like pretty much fixed what you do, but like still, it'll be nice if like somebody just said it out. To option one. Okay, what is option one again? Okay, yeah. Okay, yeah, right. So we just like keep on. So we got 111, then you got 031, then you got like 023. Then we like do it again, I guess. That's what you mean, right, Ahan? 15. Yeah, and 007. So 7 is the max we can get, it looks like. There does not seem to be any other higher thing. 007, yeah, somebody noticed. Lucky number. Yeah, okay, okay. Let me explain option two. Let me explain option two. So essentially, what option two does is, okay, say you have one and you've got like five and you've got like 20, okay, at like some stage in the game. So, like, what you do is you can like remove this one, you can pay off this one, like, you can make the zero, or like, you can, okay, wait, let me just like, instead of doing this, let me just like, wait, is this eraser or this eraser? Yeah. So 1520. What we can do is option two would make it 0. Then we swap these two. 25. Now, okay, why does this look like it is maximized? We don't know. Like essentially, like right now, and we've just what 15 minutes or like 10 minutes into the problem. Why is this better? Yeah, we can do 006 as well, I think. Wait. Do you want to like tell the wait, what's the algorithm for 006 as per you? Okay. Okay, yeah, no, wait. How did you do double 6? Wait. Okay, option 1 to B2. Okay, so you play like 103, option 2 to B1. Ah, okay, I see. It's smart. 030. Then like what you so essentially like if we have A and then we have B, then like option 1 just like we can repeatedly do option 1 and make a 0 to A plus B. I hope everybody understands this. It's like a kind of block move, like to save writing space and time. Essentially, this is what happens, and we get 006 here. Right. 006. Fine. Okay, so now we did 111. Yeah, I applied option 1 repeatedly. Option 1 A times. So like you apply option 1 3 times and you get to 006. So essentially like this is a kind of tool. Like tool 1, AB goes to 0 to A plus B. So like defining these tools in your head like, yeah, I applied one exactly. But the thing is now that you know that you have this tool, like you can just directly apply this tool and this is like a new tool you have. You can think of it like that. This will be like really useful as we come to like the rest of the problem. As we move on to the problem. Okay, 111. Okay, any other base cases somebody wants to? More base cases, please. Any suggestions? Okay, let's try, say, one. Okay, let's try one. Okay, wait. 111. Oh, wait, I'm at a huge zoom. Yeah. 1111. Yeah. So how would you try to maximize this now? So essentially you have okay, let me just like move to the side. Okay, to like make things efficient, just like tell me like no need to say option one, just say 1 comma B1 and I will apply option 1 on B1 comma this. Like that, okay. Okay, nice. Okay, so we have a change in claims also. Not fine. Sure. So let's just do a few more base cases, then we'll like come back to that claim and then let's see what we can gain from that. Okay, we use option 1 on B1. Okay, 0311. Fair enough. Then what do you think of doing? So essentially you'll have like two options. You either play this one, or you play this two. 1 comma B2. Okay, excellent. Okay, let's try 1 comma B2 now. B2 would be, oh, my bad. B2, that would make it 0303. Yes. And what do you do after that? This was what you did, right? 1 comma B2. So this is B. Wait, no. Oh, B2 means this. Okay, wait. Did I make, you cannot, wait, what? Use option 1 on B. Wait, this is B1, this is B2, this is B3, this is B4. Using option 1 on this is like not possible because option 1 needs at least one here and like you have to send two here. So like you need to remove one coin from here and send two here. So you can't use option 1 there. Do you mean to say option 1 on B2 and B3? Okay, 1 on B2 and B3. Okay, okay. Let's do that. 0, 2, 2, 3. Okay, this is what you wanted, I guess. Okay, you can do 0024. Okay, let's just quickly go through the steps and see if we can get 0024. Okay, do you mind telling us what next? 0, 0, 0, 24, sorry. I read it wrong. Wow. Then use in B3. Okay, B3. B3, comma B4, I guess. This is the one. 1, 5. Okay, sure. And then 0, I guess you just finish off one more B3 or what? I think just a Y works. Like if you're saying yes, just say Y. It just saves time answering. So I guess this is your last move. 0, 2, 0, 7. So I'll just like okay, yours. Okay, let's look at those steps as well. Okay, so let's just look at your moves. Okay, 0, 0, 0, 28 is possible. Okay, 0, 0, 0, 28 possible. Okay, let me just like finish that, then I'll come to yours. So Anirudh's, yeah. Okay, let me just like finish this. So 28. Anirudh, do you mind telling us how 28 is possible? Uh, like from here, I think you would have gotten here and then you would have gotten 28, right?
Yeah, so I changed. I got 0170 after this.
0, 1, 7, 0. Okay, you used option two.
Yeah,
And
and
then you probably just like shifted all sevens here.
uh, no, I used it again, option two again
You used option two again on which?
on the second box.
Oh, like this. Wait, you can't use option two here.
So,
Wait, you
yeah,
got to like zero.
no, wait, I got the seven there. So 1014,
Oh yeah,
0,
0, 1, 0, 40. Okay, yeah, yeah. Okay, so that's what like you move everything from like seven to the last one, 0, 1, 0, 14, and now you again use option two, I assume. So like let's just quickly like finish it up. 14, 0 and 0, 0, 0, 28. 28 is okay, wait, what? Okay, 28 looks like it's possible. So 20, like we want to like right now, like our aim is to like get it as close to like maximize our things. Then we'll see what like what changes we have to make to like optimize. So yeah, 0, 0, 0, 28 looks good. Like I think that looks like pretty. But to be honest, like, do you all not think that we are right now in like just 28? What is 28? 2 to the power, but 5. And here we have to get like, okay, so our number which we want to get is like 2 to the power 11 whole to the power 20, 10 to the power 2010, which is like huge. So we only have like two more ones on the start. Isn't that correct? So yeah, okay, so now we've gotten this base case done. Okay, now any base cases like any of you are trying, like let's try one of those. So this problem is like really like good to try base cases, like get a feel of like what moves you should make and one, what you should go. We It's 28 max. Okay, you I do not know if 28 is max, but like to be honest, the problem does not like if we are assuming the answer is yes, the problem does not need you to prove 28 is max. Like you just have to get greater than this number. So like 28 is pretty high, and then like if you can get a better thing, like sure, like please try. Okay, let's try for 5-1. Okay, okay, 5-1, sure. Okay, this is where things get interesting. A lot of moves are there here. So how can you optimize this now? Let's see. So how do you maximize this? Also, like, is it fine if I like extend class for a bit? Because like I think we started at like 45, 6:45. So like we can extend like to let's like extend to like 8:15 and then see where like this takes us. Yeah, let's try keeping like 8:15. Let's try doing till 8:15. Right. So okay, so do you guys, yeah, yeah. Okay, Ahan. You don't need to do that actually. So essentially what you want is you want exactly this much. So like we don't really right now, like our aim is not to like check every number. Like I would say like you wouldn't want to check every number. You just want to like try maximizing your gain, like your gain, like in the last box. So that's what you want to try right now. So let's not go to like what numbers below max are possible. I think that would be like a really good question. Like you could probably like try working on it afterwards, but let's try just like maximizing our moves. Because like eventually like we want to at least like go greater than 2020 to about 2010, or like we want to like at least equal it in some sense of the word equal. Now we can get 57. Okay, how can we get 57? Wait, okay. You can 28 into 2 plus 1. Okay, 28 into 2. Okay. You have one. Okay, so essentially you are going to 28. Sure. Then like what you do is 0 to 0, 0 to 8. I think that's what you do. Then you do 0, 4. Okay, you don't do that. Okay,
So
let's see
the
what
extra
you
one was at the last. What I did was in that the extra one I've put it last. So 28, and then you shift 28 to the right. So the rightmost number is 1.
give me a second. Okay, wait. Wait, do you get like do you just get this? Oh, okay, okay, okay. I see it. 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 Okay, okay. You just apply it on these four, right? You apply it on these four. You get 0, 0, 0, 2, 8. Am I right?
Yeah,
So, and then you like just use that tool we had at the bottom or whatever. And then like you get 28 into 2 plus 1, which is like 57. Yeah, but do you think this is like the best you can do, honestly? Okay, you can get four. Okay, we got a 448 also now. Okay, let me just screenshot this since like we are like I'm really lazy to like write this much down. And now let me just wait. Yeah, can I? Yeah, it works. Let me control V. And okay, we have got something for 448. Okay, let's see how this was done. 3111. Okay. Let me just write. So essentially what we did was 03111, 03031, and then we just like moved, like we used that tool to come here. This was just this was just this, 00631, and then we just like again we use tool. And wait, am I missing something? Oh yeah. Okay, we've got, yeah, don't worry, like missed steps are fine. I think we can like let's just wait, I'll just like let's just try seeing how much we have I can follow, and then like then just so 00607, 005. Yeah, yeah. Essentially, okay. So now your moves become like this. Oh wait, what? Why did it not erase? Yeah. 00570. Then you do what? Then you double this. Wait. Double into 2. 005 014. Excellent. Then you like 0, 0, then you use 5 like option 2. So this is a swap essentially. Again, you do the swap. So you get 4, 14, 0. Then you like multiply by 2, 0, 0, 4, 0, 28. And then you just like, I think like, now I hope you all understand like where we are going. So I'll just like write down the steps as he's written it. 003 056. I think that's right. 002 0112. 001 0224. I'll just trust the multiplication. 0 and we get, oh wait, not 224. Well, yeah, 224 and we got 448. Yes. And 448 is greater than 57. So we might want to pay attention to this method. So that's the kind of idea. Yeah, tool. Exactly. So we just like, so from this step to this, we just use the tool. Like 14 to 0, then 0 to 28, and then essentially we'll just like keep on like repeating this. So essentially our thing is like tool, swap, tool, and like so on. That's the idea. Okay, constructing that, okay, that is like really random. So why do you want to construct that, Swarna? Can we like understand why it would be nice to construct that? Like, what's your motivation essentially? Even if you have no motivation, it's like fine. Half of math, some like there are quite a few mathematics on which like don't. Okay. Ahan is, I think Ahan has roughly like understood like what we are trying to say. So Swarnava, like what we are trying to do is like we want to like maximize how much ever we can get from like 1 1 1 1 1 essentially. So how can we do that is the question. 0 0 0 32. Okay. So 4 zeros then 32. Okay, that's better than our 28. Yeah, so can you give us algorithm? Do you have an algorithm or do you think that we can create one? Okay, Ayush, I don't understand exactly what you're saying. Okay, yeah, okay. Okay, Ayush, like, let me just confirm. I think like we are getting slightly mixed up with the meaning of the question. Wait, yeah. Oh, it zoomed out a lot. Okay, let's just zoom in back. So essentially, what we don't really care about maximum. Like, all we want to show that we can reach exactly this number. We don't care ki this is the maximum we can reach. No. All we care about is reaching it. Since we are answering yes, like all we care about is reaching that 2010 to the power 2010 to the power 2010. So yeah, proving its maximum is not important. That's why like algorithms are so nice. You don't need to care about like proving key this is true, or you have to use some magic invariant or inequality and then you get its maximum. No, nobody really cares about that. All we care about is did you get the required result, and did you like and like how do you know your algorithm works? That's all. That's the whole fun part about algorithms. I hope you understand. Like, okay, so now I hope like everybody is kind of getting like what direction we are moving in. So, okay, let me suggest a base case now. I have suggested one or two, but like this was something I tried, I think. We are also a bit short on time, but it's okay. I'll try not to rush too much. So, yeah. So now wait, first before we move on, can somebody see what is so essentially like can somebody see okay, we had like 607, right? Wow. That is unfortunate, but okay. We had 607 and then we went to 00448. So essentially, like now, if we say we had A0B, what do you think we can reach using this method? Can you like generalize like what you'll reach? Okay, 3 into 2 to the power 2024. That is five zeros and one. Okay, you got used six and you've got Anirudh, like do you think that I don't think that's greater than 2010 to the power 2010 to the power 2010? Just asking. 2 to the power A into B. Okay, that's really okay. Six into what? Uh oh yeah, okay, I see it. 2 to the power 6 into 7. What? There's no way that's true, right? Wait, 2 to the power 6 into 7 is 448? No. 2 to the power 6 into 7 is not 448. I don't think it is. Wait, what? It is 32 into 7. Wait, 2 to the power 6 is 64. Okay, wait, maybe that is what? That's kind of like. Okay, sure. 28, 76, 40. Oh, damn, nice. So we've gotten. So A through B goes to 2 to the power A into B. Nice. So finally, we are talking sense. Like we reached like a single power. Like it's an achievement. Like earlier we were just like hanging around with like low hanging stuff, like just like 28 and stuff. Like we just reached 28 and stuff. So now that we have 2 to the power A into B, that's like good. So now okay. You had 3 into 10 to the power 2024. Okay. Wait, let's just confirm one thing. Uh, 3 into 2 to the power 2024 is like, okay, it's less than 2010 to the power 2010 to the power 2010. Yeah, it's less than that. So I think we'll have to do a bit better than that, but it's okay. That's a good, at least we got like a power of 2 to the power 2. So now let's come back to here. Okay, let's try this base case now. 3. Okay, let's try say 2 0 0 0 0. B1, B2, B3, B4, B5. How would you like try to maximize this, so as to say? O1 on B1, O1 on B2 on B. Okay, let me just. Okay, so the thing is, okay, in this base, so essentially, like these are things which I tried, and the thing is, if you'll notice, like what I'm trying in these basic cases is stuff like how do I maximize, like if like a bunch of zeros is like useless, but how much can I make this two reach in the final, in the end? So since we have like a bunch of ones, if I can just make this 0 3 1 1 1 1, my idea is that like okay 0 3 1 1 1 1 is fine, but like this is annoying. Like this is like a bunch of constants you think of. So if I like make it neater, like 0 3 0 0 0, it will look better, right? It will be like easier to handle and see what algorithms I can make. So that's the motivation to go for like 2 0 0 0 0. If you notice that like most of the time we have done like B1 to B2. So yeah, 2 to the power 2 to the power 16, I think you mean. And so essentially, like to get to this, I want to do 0, like 2 0 0 0 0 first. Then we'll do this. Right. No. Okay, just okay, so you claim that we can do from okay, so from 2 0 0 0 0, we can do 2 to the power wait. 0 0 0 0 2 to the power 16. Okay. Wait, let me just copy paste your algorithm. And then let me let's try this and then wait, let's just like wait, what happened? It hanged. Whoops. I'll have to like make it a bit faster. Control V. Okay, let's try this algorithm. O1 on B1. Okay. So this is for 2 0 0 0, right? Okay. 2 0 0 0 0 goes to Okay, so essentially, okay, so this will go 1, 2, 0, 0, 0. Do you like do the one as well? Just asking, Ahan. Oh, you don't do the one. You just leave it, huh? So it becomes okay. So you got 32 for like 1, 1, 1, 1. Didn't we get like 448? What? Like I think we have to like try maximizing. Yeah, I think you can try maximizing more than that. So yeah. So let's now come back to this. Okay, 200 goes to 32. Okay, like just tell me what you do after this. Do you do O1 and be like this? Like, do you just like use the tool at this point, or like do you do this? Like option one, like okay, yeah, so let's see. Okay, repeat tool. Okay, sure, sure, sure. Nice. Okay, let me just like yeah. Essentially 2000 becomes 04000. Then you do 00800, and then you do okay, so now we had 2 to the power a into b. Okay, now we have to like your b is like not there. So how what is your formula here? Mm. So after 00800, what is to be done? Wait, okay, do just like okay, we just do this. Okay, I can see how you get 32 now. 00016 000. Okay, this is like sure, but why not better? Like I like we got like 448 like when you did like 1111. Like we can do better.
You can take a one from the third box and you can get it to the last box.
Okay, so you are okay, so let's with 00800. I'm just asking.
Yeah, with zero
Okay.
zero. This one.
Okay, okay, nice. So let's just try that. So 8, let's just do this quickly. 7, 20, and this makes it 00704. Am I right?
Yeah.
Then what do you do?
Then you just get 2 power 7 into 4 at the last
Uh,
box.
2 to the power 7 into 4, right?
Yeah.
2 to the power
Using
9, no?
needed.
5,
Yeah.
512?
Yes.
Okay, this is not, yeah, so this is not bad, but don't you guys think we can optimize this a bit better? Like, because like what they're asking us is like 2010 to the power 2010 to the power 2010. We are only getting like 2 to the power 9 here, which is like crushed. Like even if we like maybe they can like we can magically get like a power of 2010 here, but even this guy crushes it. And even like if we remove this, like this guy also crushes it. So like we are like kind of not like beating that thing. Cool. Okay. 1 0 0 1 0 4 0 0. Okay, I see an idea here. I see an idea here. So let me just like write that down. Wait. You get you get 2 0 0 0 0. Then what do you cook? 1 2 0 0 0. Wait, what? Okay, yeah, that's correct. Then you do 1 0 4 0 0. Then you do 0 4 0 0 0. Like you can't do 0 8. You can't do 0 8. Oh, 0 0 8 0 0 what? 2 4. Okay, sure. Fair, fair, fair. Okay. Yeah, you can do that. So you just like move the entire thing there. 8. 0, 0. And like, yeah, this is the same thing which like we got earlier, I think, right? You'll probably get 2 to the power, like you'll probably maximum, you'll get like 2 to the power 9-ish or like maybe like 2 to the power 10-ish. Perhaps you won't be crossing that. Yeah, it's the same 2 to the power 9, essentially. So now let's like try thinking about what exactly the move does. So let us actually observe move 1. So this is like what move 1 does is essentially like okay, let's just like not ignore. Let's just look at this. So 1 0 goes to 2, 1 0 0 goes to like 0 2 0, and then 0 0 4. If we like just do option 1 again and again. And if you want to try, you might actually notice something very interesting. So for example, if you like look at one more case, like if we only using option ones, they're only using option ones and stuff here. 1 0 0 0, you'll get to like 0 0 2 0 0, then you'll go to 0 0 4 0, then you'll get to 0 0 0 8. So can anybody notice like what is going on? Like there is a pattern kind of thing here. So okay, I'll just do like something out of the ordinary to like draw attention to it, and this just might give it away. 1 0 0 4 1 0 0 0 9. Okay, now let's see. I can see two messages. Okay, we're getting to a power of 2. Okay, we're getting closer. Nice. But like, can you like look at the start state and look at the end state? Like, what do they signify? Wait, this was not so look at one. Exactly. Okay, like we got our magic word. Binary. Yes, yes, yes. So essentially, like if you do option 1, think of this number in like, oh, okay, it wrote. Think of this number in like binary. So like 2 to the power 0, 2 to the power 1, 2 squared, 2 cube, dollar 2 to the power n, I. And then we start off with some numbers, some list of numbers, whatever. And then whatever we do at any point, this sum is not will not change. Like if we only do option 1 moves, this sum will not change. So like it will always remain like 2 to the power I. So let's name this B1. Wait. Okay, we are okay, sure, this works. B1. Okay, let's name this AI, like instead of like B1. So this is box 1, box 2, and this is box I plus 1. This is AI minus 1, A3, A2, A1, A0. So essentially what we have is this quantity remains the same. If we only use option 1. Okay, Ayush. Okay, let me. Okay, should I just like the binary part? I think that's what you want me repeating. Okay, I'll repeat the binary part again. So essentially, like what happens is, for example, let's look at a binary number of say 1 1 0. We only do option 1 moves. So what we do is 0 3 0. Like if we do option 1 here, and then if I do like tool over here, you will get like 0. I'll just like do 2 3 steps to like make you understand what exactly they are. 2 2 0 1 4 and 0 0 6. Okay, so these are the moves which go on. And now if you look at it, like write this as 2 squared, like 2 to the power 1, 2 to the power 0. Think of it as in binary where it's kind of expanded. So for example, we just like multiply it, so as to say. Oh, yeah. Exactly. So this is 6, right? Okay. Wow. What? Okay, yeah. This is really lagging. So if you evaluate it in base 2, this is 6. 3 into 2, 4 plus 2 is 6. This is 6. I better, okay, I think I have to start rushing a bit. If you have any doubts, like just ask, but like I will go a bit faster. So this is 2 into 2 plus 2, which is like 6. This is also 6 if you calculate. And this is also magically 6 in binary. So yeah, you essentially reached this point, and now this is an in invariant if only O1 is used. Now, I would like to remind everybody about what is our state, like what we start off with. We start off with this, right? Like as per the problem statement. So if you look at the number by the invariant, yeah, exactly, option one preserves binary. So now, if you look at this number, if I just total it up, you'll get like uh, 2 to the power 6 minus 1. I think you should get like 63. Like using our invariant, this should be 63. Wait, let me just check. I'm not hallucinating. 2 to the power. Yeah. Oh, well, not 63. It's just 63. And like what we want to reach in the end is like 0, 0, 0, 0, 0, 20, 20, 20, 10 to the power 20, 10 to the power 20, 10. So now like this is, if you evaluate this, like this comes out to be 20, 10 to the power 20, 10 to the power 20, 10. So we'll have now, like you can see why any option one only moves will like fail. So we have to like definitely use option two somewhere. So let me now give you like the option two part. Yeah, what does option two do in binary? Yeah, excellent question. So now, obviously, option two will not be invariant in binary because like we want to like show that algorithm exists. We believe an algorithm exists, and if it's invariant, like we'll get to 63 to 63 only. So like it won't be. So let's just like look it up. So like 2 to the power I, 2 to the power I minus 1. I'll just like directly go to the gist of it. So you have A and you have B and you have like X. Then like what option 2 does is X minus 1, this becomes B, and this becomes A. So this evaluates to uh 2 to the power I into X. Like the rest of the number doesn't matter because it doesn't change. This is the only part of the number which changes. So that's why we are only evaluating this. It's not technically binary, I agree, but like you can think of it as like an expanded binary. Like we're allowed other digits, but like we're allowed other digits, and like a digit can have multiple representations. That's like a better explanation for it. So wait, let me just, bro, how much lag is there? Okay, so 2 to the power I into X plus 2 to the power I minus 1 into A plus 2 to the power I minus 2 into B. Let me zoom out a bit. And this is 2 to the power I into X minus 1 plus 2 to the power I minus 1 into B plus 2 to the power I minus 2 into A. So now let's subtract the 2 and see like what difference is there. So like 2 to the power I into X minus 1 minus 2 to the power I into X. So now we have 2 to the power I minus 2. Okay, no. 2 to the power I minus 1 into B minus 2 to the power I minus 2 into B. 2 to the power I minus 2 into A minus 2 to the power I minus 1 into A. This will give like 2 to the power minus 2 to the power I into x plus 2 to the power plus 2 to the power I minus 2 into b plus 2 to the power wait, no, not x, not 2 to the power I into x, sorry. Minus 2 to the power I plus 2 to the power I minus 2 into b plus 2 to the power I minus 2 into a, right? Taking 2 to the power I minus 2 common, we'll get b plus a minus 4. Is this fine with all of you? Yeah, exactly. We'll just take 2 to the power I minus 2 common to like make math easier. I hope you all agree that this is what evaluates to. So like how 2 to the power I minus 1 into b? Sorry. Okay, yeah, sure. So now we have, so now the only way, if you want to maximize it, wait, I think I've done a calculation. Oh, wait. We have an error here. We have an error here. Exactly. Nice. This will be minus because like here this is greater than this and here this is greater than this. It is not actually b plus a minus 4. It is b minus a minus 4. So it increases when b is greater than a plus 4. Okay. So essentially, like Anirudh, so what we did was we were analyzing option two in like this new binary invariant we created. And now essentially like this is what happens in option two, right? Can you confirm? So like if you evaluate in binary, you will get this. You will get this in our system. This you'll get the old binary. And this is a new binary after the move. Before, after, and now just to like see what gain we have, like I want to just examine the gain part of things because we wanted to keep on increasing because we are going from 63 to this big number. We wanted to increase. So if we look at the gain part of things, we get this 2 to the power I into x minus 1. You just subtract both of them. So if you do the math out, which is like not much, it's just algebra, so you'll get this part. So yes. B is so like it increases when B is greater than A plus 4 or B minus A is greater than 4. Whatever. So we want to do option 2 only when it's like this, like beneficial like this. So now the thing is, let me just like jump a bit. Okay, I will give you an idea for like the 3 0 0s, so 0 0 0 case. Like it is not exactly motivated by this, but you can see kind of why we would want to do option 2 in those cases. So now what we do is for 3 0 0 0 is like I'll give you the first few moves and then I'll like leave you to like try and like maximize this as much as possible. And which after which like it becomes very easy to like finish the problem. Okay, so now let's do this 2 2 0 0 0. Okay. Now what we were doing is we were just using tool and shifting this here, right? So like instead of doing that, I'll just like break it up into stuff. 2 1 2 0 0. Again, I will do the same thing. 2 1. This should be what 2 0. And then here like there's no point. Like I can't do the tool like the option one. So I'll just use the tool and I'll just make it 2 1 1 0 4. So now if you look at it, if I can like so if you notice like option 2 here, if I use option 2 here, I am still like I'm not losing anything by doing option 2 here. Because like b is greater than like b minus a is greater than equal to 4 is like no loss you can think of. And here, like, it's 4 minus 0, so no loss. So, like, this will become 2, 1, 0, 4, 0, right? Now, what you can do is 2, uh, yeah, so 2, 0, 4, 0, 0, I think. And no, don't. Yeah, yeah. So the thing is, I don't want to do option one right now because like I can like since I'm getting no loss, I can just like keep on pulling the four in front, and then I can use like option one to like maximize it towards the end to make it like easier and more handy. So 20400, and now what I do is oh wait, yeah. Now I'll do like so two. Now this now here comes like the slightly more random part. So now I just split the two up. 12400. Essentially, what I want to do is, you'll probably like after a while you'll probably get 100 A0. Like if you had done the only option two and move tool thing, but like what I want to do is instead keep it at like 1110 So like I can just cancel this out, like move the A here, gain something, then again cancel this, move the A here, gain something, then like again like just keep on doing this. So that's our aim. Like, so essentially, we are leaving back a trail of some sorts so that we can push stuff in front. I'm sorry if I'm going too fast, but yeah. Okay, so now let's see 12400 and then 12320 and 12304. Now, what you do is 1, 2, so essentially, like tool and 12304, 1, 2, 240, no loss. We've not lost anything till now, really. Now we just now we just like 12208 we get. Now notice here that now if I do this, I gain because b minus a is equal to 8, which is greater than 4. So I gain quite a bit, in fact. And this comes to 12180. So again, like I do the same thing, like 1 2 1 2 1 2 1 0 1 6. Again, I go for a gain. It's like 1 2 0 16 0. Right? Nothing large, but I've made some gain. So now again we like so we've like 1 2 0 16 0. So like we go for something like 1 split 2. Yeah, yeah, yeah. Okay, so let's do that. 1 wait. Yeah, no, like split 2 as in like just like let's just move the 16 in front because we'll get gain. We gain something. So make this 1 and make the 16 0 0. And now we like 1. Okay, we just make it 1 1. Then we make 16 to like 15. And then we make it like 15 2 0. Then like 1 1 15 0 4. 1 1 14 4 0. 1 1 what is 1 1 14 0 8. And essentially I keep on doing this until I get like 1 1 1 0 2 to the power this was 14, this was 2 to the power 3, so I should get 2 to the power 16. 1 1 16. How do you get 16? What? So essentially, like what you want to do is like you want to like keep on like having this chain over here. You want a chain of some sort. Oh, sorry. You want a chain here, and then you want to like be able to pull this number back to the front. maximizing gain. How do I know I can reach this number? Okay, let me just show you. So essentially, if you look at it, like this is what 111408. So I just repeat this process again. Uh, so this process is swap, then tool, swap, then tool. So here, if you notice, it was 1504, which is like so 15, and this is 2 squared. So 15 plus 2 squared is equal to 17. Here, if you notice, it is 14 plus 2 cube, which is equal to 17. So like it'll keep on being 17 throughout this process, and eventually we'll reach this, which is like pretty big. So now again, I just like keep on pulling it back. And then again, 102 to the power 16, 0, 0. Uh, so yeah, I can see a message here. Yeah, now what we do is, one second. Yeah, one. Now we can again do this process. So essentially, if you look at it, 1, 0, 2 to the power 16, 0, minus 1, 0, 4. This is what it becomes, right? So if I remember correctly, we had like a formula, we had a kind of formula, like we can be like, okay, so the formula was like 2 to the power A into B, right? You guys can confirm. So 1, 0. I won't go to the end. I'll just like leave it at 1. So I could have, so it'll be like 2 to the power, this will go to 2 to the power 16 minus 1, and you'll go to like 4 times 2 to the power, 2 to the power 16, 2 square. Yeah, you'll reach this. 4 times 2 to the power 16, I think. Wait, no. So you'll get something really big. Like, let's just assume it's like 2 or something. Like, you'll get some huge number again. And now what you do is like you again, since you have a 1 here, you just like swap it back. Like now we have 2 to the power 16 minus 2, 0. And then now we have 1 here. So like we move, so like 0, 0, 1, 2 to the power 2 to the power 16. And now we again, now we just move this because otherwise we don't have any, like, we don't want to double it. It's not useful to our binary. So we do 0, 2, 0, a into 2 to the power 6, 2 to the power 16 minus 2, 0. And now I think you kind of see what our process is doing. Why 4? See, the thing is, when we do this, right, 2 to the power 16 minus 208, right? We don't increase the binary. We don't increase the binary at all. Like that binary sum we created is not increasing because they're only doing option 1. But like if I like do the swap at the correct timing, like it does increase by like a decent bit. Like it increases, in fact, by 2 to the power I minus 1 times like b minus a minus 4, which is like if I is like pretty large and like this is large, like this is much, like you can already see we have 2 to the power 2 to the power 16, and we still have like 2's lying over. So like the thing is that if you like just shift the two, like option 1, only the binary sum is increasing, which is like not really that nice. I hope you're like trying to get, yeah, like hope you're getting the feel of what I'm saying, like what I'm trying to say. Okay, I'll just show it to you. Uh, let's just try making it one more toolbar and then like maybe you might understand. So, okay, so now we have, does this generalize? Let me just show you 0, 2, 0, 2 to the power 16. Let's just assume it's this because like there's some constant factor which is like tiny, but like sure. This, and now what you can do is 0, 1, 2 to the power 16, 0, 0. And now if you again do the process, oh no, this will not. Like you just move the 4 there, like you move a 4 here. So this is like minus 1, this will become 4, and now you will get 0, 1, and then you'll get 1, and you'll get like 2 to the power, 2 to the power, 2 to the power, like 16. Are you getting it? Like, I'm getting this huge, like, they're getting a power tower essentially. If you can see what I'm getting at. Like, does it make sense? Like, you can just, in fact, like, you'll have to do it a few times, like, convince yourself, okay, this is true. And unfortunately didn't have the time in the class to, like, fully, like, convince you. Like, you can ask doubts. Like, you can surely message me. Yeah, but by the time the one gets eaten, okay, sure. So, by the time the one gets eaten, like, your two sequence will be, like, at least, like, 0, 2, 2, 2, 0, 16, 0. Then you'll get like 0, 2, 2, 2, 2, 2 to the power 16, 0, 0. Right. So one gets eaten, and you'll get like one more big power tower. So what do you think is larger? So like this or like 2010 to the power? So let's like try. In fact, like I have not used, in fact, like if you look at it, like I have like not even used, I just used 3000. Like I used this. I did not use like 11111. And like if we use this, like you'll actually get something larger. Like you'll get 31111, which is like greater than this. And this is generating 2 to the power, 2 to the power, 2 to the power. How many twos? I've lost track. Four twos. And then a 16. So now let's just check. Like, okay, so do you know how log works? Like logarithmic stuff. So like what we just do is like we just like keep on taking log. So essentially like let me just come to the side. So we had four twos. And then we had 2010 to the power 2010 to the power 2010. Now we just like keep on taking logs, and then let's see which is larger. So log 2 will take log 2. So if we do this once, then we'll get 2 to the power 2 to the power 2 to the power 16 into 1. And this will become log 2 is like 2010 is like less than 2 to the power 11, I think. So like the power tower comes, like this thing comes down into like 2 is like into 11. Is this, do you like understand? Okay, this is like greater than this. Yeah, yeah. So our original claim is actually like false, because like we can never reach an infinite value. Like an infinitely large is not value is not possible if you have like a finite number of like coins, because eventually the process must terminate. And the thing is like if it terminates at some value, like you can't get higher than that. So like essentially like that is what will happen. So you can't get like, wait, where was that? Where are we? Yeah. We can't like do like that huge stuff. So like we can't like touch like every large number, but we can get sufficiently large to just like win the, so just like beat 2010 to the power 2010 to the power 2010. So I'll just like do the logs to like convince you ki we are on good hands. Then we get 2 to the power 2 to the power 16, and this becomes uh 20 2 log 11 is like what? 4. So like if we take log 11 plus like 2010 into log 11. Like, okay, so now this is like what, 4. You can already see like this is like way larger than this. Like it's just like, okay, let's just like be nice. And then like this is like 2 to the power like 1024 at least. And then like this is like not even 5 digits. So like we have gotten something which is like much, much, much larger than like 2010 to the power 2010 to the power 2010. And now, like, if you like actually work out with the 3111, like if you work with this instead, I'll leave it to you to show it. Uh, you can get a number which is like, wait, how large was that? Wait, have I not written it? What? That is so unfortunate. Wait, I should have written it somewhere. Okay, I think you can get 2 to the power 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 2 to the, I think we get like 8 or 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, and then you get like 13 or like something like that. So if you like use this and you like optimize your moves even further, you can get this. Yeah, so like this thing, like the thing is like once you get the idea, it's like really easy to like maximize it. But before that, like you will feel like it's like not going to reach that power. So you can actually like reach this number. Like I have like checked and seen, but you can actually reach this number if you thought it was set. So yeah, I think that will be. So now okay, so now of course we've now gotten arbitrary large numbers. The thing is, yeah, so we want exactly this, right? This was actually like something I deliberately did not want to like show you so that like you don't get like diverted key exactly. We want all the minimum numbers. So like the fact is that to make this, I'll actually leave it up to you. Like I think this is quite much more doable. You can think of it as like homework. So like yeah, sure, sure. Please. I hope you had fun. And so like what I wanted to do is given that you can reach this number, you can reach something greater than 2010 to the power 2010 to the power 2010, right? So now like try to reach exactly this. And that is like your yeah, you can probably reach everything below it. I have not tried, but you can definitely exactly reach this number. Like you can exactly reach this number that I'm sure of. So I invite like I will leave this up to you. Since like the hard part is like getting to that large is like the hardest part. Like just now try to see like how you can like reach this number. Okay. Okay, it's like 8:45. I think it's time we wrap up. So I think I'll send all this on the OMC group and stuff. And yeah, thanks for joining. I hope you guys had fun and see you then. Yeah. Bye. Bye, Jasmith. Thanks for attending, Ahan. Thanks for attending, Jasmith. Who else? Oh, Anil left. Thanks to him as well. And okay. I hope you all had fun. Good night. I think I'll wrap up now, Shreya. Wait. I think we can just like stop the recording. How do you stop recording? Stop share and recordings. Stop recording, sure.